Hello and welcome to Numeristical. This is the fourth and final video in the series on the fundamentals of gradient boosting. So if you'll recall in the first video we talked about decision trees and how those work. Then we talked about how to take an ensemble of those trees and add randomness to make them a little bit different, make every tree a little bit different. That was a random forest. In the last video we talked about the gradient boosting algorithm itself, so how we build these trees where each tree is fit to the gradient of the loss function of the previous model, and so how that progressively sort of corrects the errors of the previous model and gives a more powerful technique. Now along the way we saw that there are lots of these little settings that you have to pick in gradient boosting. How deep do you build the trees, how many trees, how big is your step size, plus all the parameters about the decision tree itself. So there's a lot of these knobs, so to speak, that are called hyperparameters. So in this video we're going to really get in depth about what all those hyperparameters mean and how to set them, with some special attention on how do you set the most important ones. So that'll be today's video. And just to let you know, after this, we're going to start a new series on building gradient boosting models. That'll be much more hands-on. We'll have Jupyter notebooks, and we're really going to go through and apply everything that we learned in this set of videos. We're going to go ahead and apply those and really talk about real-world issues that come up when you try to build these models. So I hope you'll start getting excited about that one. Before we get into today's lecture though, I'd like to ask you again if you could please like the video and subscribe to the channel, because that really helps me out. And with that said, let's get into the video. Next, we're going to talk about the different hyperparameters involved in the gradient boosting algorithm. So there are many knobs that can be adjusted in the gradient boosting algorithm. So what do I mean by a knob? Well, we talked about how in the gradient boosting algorithm, you're going to build trees of a certain depth, and you're going to add them with a step size of a certain amount. You're going to run a certain number of trees, and then beyond that, we talked about the other settings that we had, for example, in random forests and in the individual decision trees. Those are all going to be applicable to the gradient boosting algorithm overall. So there are lots of different settings that will affect the details of how this algorithm runs in practice. Now, the goal of most of these knobs, and a good way to think about them, is they're providing ways for you to balance overfitting and underfitting. And it's hard to know ahead of time what are the right settings of these knobs that'll give you that good balance between the two. And it's going to be very problem dependent. For some problems where there's very rich signal and you have a very large data set, you're going to tend to be able to put them in a place. If there's more signal to be found, then you can use more aggressive settings, which will be more likely to overfit on a smaller problem, but might still extract signal on a bigger, more complicated problem. So unlike a random forest, gradient boosting will generally overfit to the training set. If you just run a large number of trees and you just let it keep going and keep going, eventually it'll start making individual corrections to every particular data point that won't really have any signal behind it. They won't be finding any general principles about the mechanism that generated the data. Rather, they'll just be fitting the peculiarities of each data point. So we're going to use this term regularization, and here we're going to use it just to refer to ways. What are the ways we can make it hard for the algorithm to overfit while still allowing it to extract meaningful signal? And so what are some examples of this? Well, if you have shallower trees, for example, it will be harder for the algorithm to overfit because it can't make the tree so deep that it's just a very few data points or even a single data point in a leaf. If you randomize the data, if you use a different data set of each tree, it's going to be a little harder to overfit because the correction that you made for one data point in the next tree, that data point might not be in the data set. So that randomness will make it harder for it to make these very customized corrections that are just correcting the idiosyncrasies of an individual point. So these are the kinds of things you should keep in mind as we talk about these hyperparameters and talk about how you want to set them. So what are the different types of hyperparameters involved? We're going to try to come up with different categories of hyperparameters to help us understand the landscape. So there are hyperparameters that are related to the learning rate and the number of trees, the size of the decision tree, the sampling of the data for each tree, as in the random forest, the sampling of the features used at each node or each tree, as in the random forest. Then these adjustments to the loss function. So some loss functions incorporate regularization inside of them. These are now very common, and so we'll talk about that when we get to that section. Now, the exact names of these hyperparameters will vary from package to package. I've tried to use the most standard names, but in most cases, it's not too difficult to figure out how to map the name from one function to from one package to another package. We're going to start by focusing on what I'll call the big three hyperparameters. These are the three that I think are most important to get right and are kind of an order of magnitude, I would say, more important than the rest. So the big three hyperparameters. And again, these are the most crucial ones to get right, are the max depth of the decision tree. Now, some packages, they might not use max depth, they might even use number of leaves or something similar, but basically this is how big is your decision tree? How many decision points are there in it? And generally, the bigger the decision tree, the more likely it is to overfit, and the less likely it is to underfit. So underfit means when there was more signal that you could have extracted, but you didn't because you made the model a bit too simple. The learning rate, we talked about this before, this is the step size. When you add each tree, what's the coefficient you multiply it by before adding it to the rest of the model? In general, a high learning rate will be more likely to overfit. You're going to take these bigger jumps, so it's more likely to sort of behave a little bit erratically. Whereas a small learning rate, the concern is that it may require many, many trees to get to the optimal model, so it might just be very slow to run. And then there's the n estimators of the number of trees. So again, we said if you let the number of trees just grow bigger and bigger, you will almost certainly overfit. So you have to get the number of trees right. These three are, I would say, have the biggest impact on the performance, and they're also highly interactive. Now, what do I mean by interactive? What I mean is how you set one of these will strongly affect how you set the other two. So for example, I might have a learning rate and a number of estimators that works really well for max depth 3, but if I make the max depth 5, that might be the totally wrong number to use. And this makes sense, right? If you, certainly for the learning rate and the number of estimators, if you're taking smaller steps, you are going to need more trees to get to that final place that's the optimal level of performance. And if you have a higher learning rate, you're taking bigger steps, you're going to overfit more quickly, so you're going to have to use fewer trees. And similarly, the max depth of the decision tree, the deeper the tree, kind of the more different scenarios you're fitting within a single tree, right? If I've got a tree of depth 2, I'm only fitting 4 different situations. But if I have a tree of depth 5, I'm fitting 32 different leaves potentially. So the more complicated the tree, the fewer of them you are going to need before you start overfitting. So this makes it challenging to set these parameters because you can't just say, oh, I know for this problem this is the right value. For this, this problem needs 1,000 trees. The number 1,000 trees might be right for one max depth and one learning rate, but totally wrong for a different max depth and learning rate. So the good news about these big three is that you can use early stopping. This is a technique, and that will simplify the setting of the learning rate and the number of estimators. And we'll talk about this technique, but it's highly recommended. And basically what you do is if you use a low learning rate and you look at an outside validation set and you basically run the model until it starts getting worse on a separate set of data that's not the training data. And that's an effective technique that avoids you having to sort of try different combinations of learning rate and number of estimators. So we'll discuss that in a future course. Okay, so those were the big three parameters. Now let's talk about some of the other categories of parameters. So there are ones that are around data sampling. So as we saw before in the random forest, the convention is to choose your data sample of size n with replacement. So n is the number of training data points you have in general. You choose in random forest, the convention is if you've got 1,000 points in your training set, you'll choose a sample of size 1,000 with replacement. So some data points will be oversampled and some data points will not be in the sample at all. In gradient boosting, the convention, the sort of most standard way to run it, is to just use the full data set every time. And this doesn't give us problems the way it would in the random forest because our target is changing. So remember, every time we add another tree to the model, we compute those gradients of the loss function for each training point. So we're going to fit a different thing every time. So we don't have to worry about all our trees being the same because the number that we're trying to fit is going to change, and that by itself will force the trees to change. We won't get the same tree every time the way we might in random forest. Now, despite this being the convention, it does sometimes help regularize to randomly sample the data points. So if I choose, for example, 70% of my data and I just fit the tree on that, it will be harder for gradient boosting to sort of overcorrect to one or a few data points because those data points will not be in the tree every time, and when it's not in the tree, it'll make some other correction that doesn't apply to those data points. So the parameters involved with data sampling are subsample, and that is the fraction of data to use in each tree, and replacement, whether you should choose this sample with or without replacement. So in random forest, the convention would be to have subsample equals 1. You're choosing the size of your data set is the same as your original data set, but replacement would be true. You're choosing it with replacement. In gradient boosting, the convention is to, again, use subsample equals 1, but without replacement. But you could also say, pick subsample equals 7 without replacement. And in this case, you're choosing a simple random sample of 70% of your data for each tree. Another reason to think about using this parameter is that it also will speed up runtime. So if you've got a very, very big data set, it may take a very long time to run each tree on all of the data. But at the same time, you don't want to just throw away your data completely and only use, say, half the training set because you want to sort of make use of all of the data. So one compromise might be, I'll use the really big data set, but for each tree, I'm only going to use half of the data. And this way, the forest as a whole gets to look at all of the data, but any particular tree will only be looking at half of the data, and so that will speed up the runtime. Next, we're going to talk about the feature sampling hyperparameter. So again, this came from the random forest. If you remember, in the random forest, you're going to choose a subset of features at each node. And this is to add randomness to the tree generation. For the random forest, this is crucial because each tree is generated independently, and the idea is that we want to have a variety of different trees to give a variety of different perspectives. And this was really the crucial way that we added randomness in the random forest. Now, in gradient boosting, again, the convention is to just check all the features all the time because our target is changing, so we don't have to rely on this sort of trick in order to guarantee that we're not just choosing the same tree every time. But again, just like with the row sampling, it does sometimes help regularize to randomly sample the features. Again, it will be harder to overfit if you can't always find the same particular combination that leads to a particular data point, a particular small subset of data points. If that's not available every time, because you only have a subset of the features every time, it'll make it harder for that to overfit. So the main parameter here is called, in boosting, typically called something like call sample by node, and that's what fraction of the features you would use at each node. Now, many of the packages also give you the option of adding by tree or by level. So at its most extreme, you could say I'm going to choose half the features for each tree. Then of that half, I could choose another fraction, let's say another 40% to choose at each level. And then from there, choose another fraction of what remains, say 50% again, at each node. So this is a bit overkill to do node and tree and level. Usually by node is sufficient. Occasionally I might play around with doing by tree and by node. But either way, these are a few noms that you can set that guarantee that at each node, you're only looking at a subset of the universe of features. And like in row sampling, this feature sampling can also be used to speed up the runtime. If I have lots and lots of features and I don't want to just throw away the features, but I don't want to have to search this large number of features every time, I can say, hey, just look at 20% of the features every time, and that will speed up the running considerably. And so it's a nice compromise often between reducing your data entirely and having to run the full algorithm on the full data set. Finally, there are a set of hyperparameters that relate to the loss function. Now, starting with XGBoost. XGBoost was a gradient boosting package, very, very popular, very famous one. And there were lots of innovations that came out in XGBoost. And one of them was to use a loss function that incorporates model complexity inside the loss function. So in XGBoost, if you're using something like mean squared error, it'll look at mean squared error, but then it'll also have these penalties for model complexity built into the loss function. So these penalized loss functions balance how well you're fitting the data with smaller coefficients. When I say coefficients, I mean the leaf values, the values output by the tree, and simpler trees being basically smaller, fewer leaves, less deep. So if you've worked with penalized regression methods like lasso or ridge regression, this is the same idea. In lasso and in ridge regression, you have a loss function which incorporates both. You want the function to fit the data well, but you also want the coefficients in the case of regression to be small. You favor, all else being equal, you favor smaller coefficients to larger coefficients. And you've got this nuisance parameter, which helps you tune between how do you want to balance the coefficient penalty with how well it fits the data. So going back to gradient boosting and hyperparameters, this leads to the following parameters. There's one called gamma, and gamma refers to the penalty for the number of nodes in the tree. So in this loss function that XGBoost came up with, they said, if I want to put a penalty for the number of leaves in a tree. Now, every time I make a split, I'm adding one more leaf, right? Because the current node would be a leaf, but instead I'm turning that one leaf into 2 leaves. So they came up with the idea to say, if I'm making a split and it didn't really improve things that much, I should probably just leave it out. And so how much improvement do I need to see for it to be worth making this extra split? And that leads to this number gamma. So as you increase the value of gamma, it will require more improvement to make a split, so it'll generally make the tree smaller. So another way to think about gamma is don't split unless you have a certain amount of gain. And that certain amount of gain, this threshold that you need in order to make the split, is governed by the parameter of gamma. There's also a parameter called reg alpha. That's an L1 penalty on the leaf value. So again, going back to the analogy with lasso and ridge regression, lasso and ridge regression are very similar, except that lasso puts an L1 penalty, so it puts a penalty on the absolute value of the coefficient, whereas ridge regression was an L2 penalty. It was a penalty on the coefficient squared. So reg alpha puts an L1 penalty on the leaf value, and reg lambda gives an L2 penalty. on the leaf value. And again, the leaf value is the value that you output. And it kind of makes sense. So if the leaf is outputting a value of 0, you're not really changing from the previous model. You're saying leave the points that go to this leaf alone. So it kind of makes sense to say the bigger these leaf values are, the more impact you're having on the model. And so we're going to sort of penalize that a little bit. We're going to be a little more conservative about how much impact we want to have. Thanks for watching. Hope you found that helpful. Again, next we're going to kick off a series on building gradient boosting models that'll be really hands-on and really focus on a lot of the important practical details that go into building these models. So I hope to see you watching those videos. Again, once more, before you sign off, I'd like to ask if you could please like the video and subscribe to the channel, because it'll really help me out. And have a great day, and hope to see you watching the next video.